Hey ho, in this video we're going to have a look at a bunch of equations that have logarithms in them and solve for x effectively. Uh, a lot of them have a very similar approach to them. Some of them use log laws, some of them use the basic definition of a log. So let's get into it. So here we have log base 5, 2x minus 3 equal to 3. So I would just simply rewrite this using the basic definition. So that means base to the answer equals this thing here. So we would have 2x minus 3 is equal to 5 to the power of 3. 5 5s are 25 times 5 is 125. So we've got 2x minus 3 equals 125. Add 3 to both sides to get 2x is equal to 128. And then divide both sides by 2 to get x equal to 64. So there you go. There's the answer. X equals 64. Example 2, log base x. So now we've got the unknown in the base, but we can still work this out. So that means x to the power of negative 2 is equal to 1 on 25. Okay, I can see that 25 is a square number already, so I can see where we're headed here. I might just do, there's just a few ways you can do it from here, but I think I might just go 1 on x squared is equal to 1 on 25. Therefore, equating denominators this time, x squared equals 25 and x equals plus or minus 5 is how we'd normally write it. And I haven't explained this to you before, but if you remember with our exponent graphs, a couldn't be a negative number for reasons that I went into at the time. Similarly here, log base a, the a can't be a negative number either. So although x is equal to positive or negative 5, x must equal 5, as it can't equal negative 5. Okay, as log base negative 5 does not exist. All right, example 3 is looking a little bit more complicated, but we can do this. We've got 3 log base 10 x minus 1 equals log base 10 8. Now you might be tempted to sort of equate the arguments, the thing inside the log here, x minus 1 and 8, but you can't do that with a 3 hanging out. I can't divide out the 3 or subtract the 3. If I divide 3 here, it does get rid of it, but then I'm left with an over 3 here, so it only just shifts the problem, not gets rid of it. Similarly, you can't subtract 3 because there's no addition here. What you can do is you can use the log law in reverse. That is log base a of x to the power of p equals p log base a x. Okay, so we're going to use it that way. So our next line will be log base 10 x minus 1 all cubed, and it means the whole of x minus 1 is cubed. Okay, and it's not the log that's cubed, it's the argument that's cubed, equals log base 10 of 8. By the way, I've got the base 10 in there because that's what the textbook does, but remember, it's implied, so we could have just written log without the 10 there. Now that we have log base 10 on the left and log base 10 on the right, now we can equate the arguments of the logarithm function. So therefore, x minus 1 cubed must equal 8. Now I can cube root both sides to get x minus 1 is equal to 2. Remember, it's not plus or minus 2 with odd powers because negative 2 all cubed would be negative 8. But we're given a positive 8, so it must have started with a positive 2. And then add 1 to both sides to get x is equal to 3. Done. Example 4. Oh, I didn't write it in. Let me just go to the textbook and work out which one I cleverly decided I would go for. So example 4 is 13F question 2a, and that is 5 to the power of 2x minus 1 is equal to 90. Okay, and the instructions in the textbook are that you are to solve for x to 2 decimal places because there's only a limited amount of things we can do at this point. So first of all, I'm going to use the basic definition of my log to rewrite this. So I'll have 2x minus 1, which is the power, the exponent, is equal to log of the base, which was 5. So log base 5 of 90. Now, there's things I could do to try and manipulate this without a calculator, like 90 is 5 times, what is it? I'm having a mental blank here, 5 times 18. But I don't think it's really going to help. So I think it's calculator time, to be perfectly honest. So I'm just going to use my, no, I can't use that. I'll just use my graphics display calculator. So I'll have to fire that up because I didn't do it beforehand. And I'm just going to put in my graphics display calculator. using the log button. This is a good video, isn't it? This is where you hit the fast forward button until you get further ahead, because I can't be bothered cutting the video down. I know it's harsh, isn't it? Okay, so I'm going to add a calculator, and I'm going to use the log button here. So Control Log, it's base 5, and the value is 90, and it's 2.79589. 79589. Now it says to 2 decimal places. I'll quickly switch over for a second back to the graph. Oh, sorry, to the notes. 2.79589. Now, just be mindful. I chose this example because I wanted you to remember what the name of the game here is. And to solve an equation, we're trying to work out what x is. We don't have x yet. All we have is 2x minus 1. So I'm going to have to add 1 to that. So I can do that without a calculator, I reckon. And now I can divide by 2. Okay, so that's what I need to work out. So I'll go back to my calculator. So I'll go plus 1, and then I'll go divided by 2. And I get 1.89794. Okay, so just looking at it on the screen here, it says, I think it says 2 decimal places in the textbook. The second decimal place is a 9. I look to the next one, it's a 7. So that means that gets rounded to 10, and 10 at one place value is 1 at the next. So it's actually going to be 1.90. And it's one of those very rare occasions where you put in an end 0 after a decimal point, and it demonstrates to the reader that you rounded in some way. Okay, so that's basically it. 1.90 is the answer there. The fifth and final example is from 13F question 4C, and it's a sketching problem. But now we can do a little bit more work with our sketching than we did before. So sketch f of x equals 3 times 10 to the power of x minus 5. Now, the first thing I'll just point out is that this is a transformation of a base graph. So 10 to the power of x is your base graph. And so remember that the base graph for a growth, as you can see, because it's 10 to the power of positive x there. So for a growth is going to be looking like that. That's the base graph. But it has been shifted down 5 units, and it has also been dilated by 3. So it's growing faster, but it's been shifted down. So our graph is going to look like this. Actually, I'll do that a little bit more centered like so. Now, remember that the vertical shift gives us our new asymptote. So I'm going to draw that in. And that's y equals -5, like so. That's the asymptote. Now, you can do this in your head, or you can do it by transformation, but basically it cuts through the x-axis. Well, let's just draw the line in first. It's probably easier. So that means we're going to have something like this, and we just need to work out our 2 intercepts here. So the x-intercept, sorry, we'll do the y-intercept, it's easier. The y-intercept is here, and it's when x equals 0, right? So x equals 0 means 10 to the power of 0, which is 1. 3 minus 5 is -2. I don't like my graph here. It's not very good, is it? But it's -2 there. This is the bit which is a little bit different because it's now a value that's not quite the usual. So we solve it in the same way as we have ever since term 1. We set y equal to 0, and then we solve for x. So we'll have 3 multiplied by 10 to the power of x minus 5 is equal to 0. Add 5 to both sides, get 3 times 10 to the power of x is equal to 5. Divide by 3 to get 10 to the power of x is equal to 5 over 3. And now we can work out what x is. We can say that x is equal to log base 10 of 5/3. Or it's log 5 minus log 3. That's the exact answer, and if you're not given any other information, you could certainly write the x-intercept down as log of 5/3. However, just for a sense of calculator skills, I'm going to put it in here. So I'm going to go control log base 10 of 5 divided by 3, and I get approximately 0.22, approximately. So I can go to my graph. Oh, you can't see it, sorry. I can go to my graph and I can put in 0.22. Or if you want the exact one, you could put log 5/3, and you'll find that that is the way it's written in the textbook as well. Again, I just want to point out this for the notes, I've written both down, but in practice, you would only write one. Approximation, if that's all that's needed, or the log, if you need an exact value. Either is okay, but always follow the instructions given to you in the question if there is one. I just want to point out here while I've got you, is that if I go log, try that again. If I go log base 10 of 5 minus the log of base 10 of 3, we would hope it would give us the same value again. We'd hope it would give us the same thing. And it does. It's exactly the same value. This is just to confirm numerically that that division rule works. Okay, I think that's enough for this video. Have a go at doing some practice problems yourself, and I'll see you next video.